significantly harder. And I never really know when that's going to happen until it happens. So, yeah. We do need a different technique for the indeterminate powers, though, so I'll warn you that. But we'll get back to that. So here's one that we haven't done anything quite yet, like example 14. Maybe, how about this, limit as x, actually this is not in the homework, but this would be kind of similar to problem 291, but it's different. So suppose I have like tangent of px divided by the tangent of qx. And here p and q not equal to 0 constants, okay? So I would say this example is somewhat akin to problem 291, but problem 291 is like a ratio of sines, okay? So what's the deal with tangent as x goes to 0? What you got? Hmm? 0? Yeah, tangent of 0, 0. That's right. So this is type what? Type 0 of 0. So what do? I L'Hopital. So L'Hopital, limit type 0 of 0. Limit as x goes to 0 of, there we go, we got secant squared, right? Derivative of tangent is secant squared. And then we've got times p, right? Because of the chain rule. And then in the denominator, we've got secant squared qx times q, right? And we're done. See, because what is secant of 0? Secant is 1 over cosine, right? What's cosine of 0? Cosine of 0 is 1. So secant squared of 0 is 1 squared, which is also known as 1. So this just simplifies to p over q. So that's not too bad, is it? Let's try another one here. What if instead of having tangent, we had inverse tangent? And let's take the limit as x goes to infinity of, say, inverse tangent of ax over inverse tangent of, bx. All right, let's try this out here. So, all right, L'Hopital, and then I get what? I get a over, limit, right? As x goes to infinity of a over 1 plus ax quantity squared divided by b over 1 plus bx quantity squared, all right? Which I suppose simplifies to 1 plus bx quantity squared divided by 1 plus ax quantity squared times a over b, which I guess would give me b squared a over a squared b, also known as b over a. What do you guys think of this example? Let's try it out. Why don't you put, say, let's put a equals to 1 and b equals to 2. What does inverse tangent of x go to? What does inverse tangent of 2x go to as x goes to infinity? What's the limit as x goes to, what's the limit as theta goes to infinity of inverse tangent theta equal to anyway? Not almost. So the graph of tangent, remember, is this, right? From pi over 2 to minus pi over 2, right? So the graph of inverse tangent has horizontal asymptotes at pi over 2 and minus pi over 2. So this is the graph of, y equals inverse tangent of theta. So both of these limits are pi over 2. See, because whether you're going, any way you slice it, whether x is going to infinity, well, 2x also goes to infinity. It's the same limit. They're both going to pi over 2. So what's the real answer to this question? See, this is just, if you'll allow me the short manga style correction, this is just equal to pi over 2 divided by pi over 2. See, because this goes to pi over 2, and that goes to pi over 2, so the answer is 1. The answer is not B over A. Just because I differentiate something and do some algebra that you're a little bit lost in, or maybe you understood it, I don't know, right? Maybe you understood it. That doesn't make it right, right? Just because somebody throws a bunch of math at you doesn't make some argument right. It's an important lesson for life, People often hide lies in mathematics, especially statistics. But anyway, the bogus step here is the L'Hopital. L'Hopital's rule does not apply in this example. Why? This is not type 0 over 0. This is not type infinity over infinity. Both of the limits of the numerator and the denominator separately exist. They're both pi over 2. This step right here is total nonsense. But it looked very believable to you guys, didn't it? Right? Because that's what we've been doing for the last 15 examples practically, right? Well, 10 examples. So just because we have L'Hopital's rule doesn't mean that we have to use it. We have to use it wisely. We have to use it where it applies. It applies to limits of type 0 over 0 or infinity over infinity. Not just anything. But I think that's a pretty good place for us to stop today. You guys can go outside and enjoy the weather. Something like that. Thanks, everybody.